So for today, I'm going to talk about LLMCAM, which is the project that utilizes GPT function calling to actually commands the GPT to execute the functions that are originally you need to code, or like developers need to get involved. So for this, this is one of the resulting products. So we have the documentation on this site here, ninjalabo.ai/LLMCAM. And then we are going to cover all of core modules today, and hopefully some other functions from utilities. So here's some basic information. So how to use, we're like importing from the library LLMCAM and then your modules here. So for the structure, we're going to have 4 modules, 4 main modules. So the core, which is the core module for implementing GPT function calling, so that allows GPT messages to execute Python functions. And then next one is the utils, which is the model for implementing utilities as compatible functions for this GPT function calling framework. Next is the vision, which is the module our special module specializing in implementing computer vision features. And these are also implemented as compatible functions for GPT function calling. And lastly, we have the application, which is the module for implementing our web service. So the web service is already deployed here on the llmcam.ninja.labo.ai, so we can try it out later when the demo day in the workshop, hands-on workshop. And now for today's, I'm going to cover the core function, which implements the function calling framework. So this contains the execute function calling, which allows GPT to execute the function itself. And then it also have the function to schema, so converting a existing Python function to a GPT compatible schema, and also OAS, which is Open API specification file, into a compatible schema. And then I'm going to cover some more complex LLMCAM utilities, including notification and store if time allows. And here is the notebook. So again, these are the index, which is the introduction that I have went through. So let's start right with the function calling. So the summary of this process, which is executing function calling from GPT messages, is presented as a graph right here. So you have the preparation phase. That is, end goal is to generate a GPT compatible schema with either a Python function or an API service that has Open API specification file. From that, you input this GPT compatible tool schema into the GPT, and it will execute in 3 main parts. So you will have number one is tool call. That is when the user has a prompt, GPT will also answer with a tool call. So this tool call is kind of a package of information that includes which tool to use, that is the tool name, and which arguments to use. Then from this point on, this is our implementation. So we will use these information from the tool call to either directly execute the function or to use a fix-up execution with some metadata. And then from these executions, we will have the result, which is again formed into a new message and then feed it back into the GPT. From then, the GPT will once again interpret the results of this execution and return the final message to the user. So we can follow this process with an example that we have right here. So first is the tool call itself. Let's see how that works. So we have right here is a function of getting weather information. So the arguments that is used in this function are the city and zip code. And then it just returns some mock data. So we manually define the tools. So we can have the name. We need to specify the name of this tool, which is the function name. We need to specify the descriptions. And then for the parameters, we have the city and zip code. So now we're going to use these tools to feed into the OpenAI API right here, that is chat completion. So we also input the prompts, which is includes the system prompt, which is you can get weather information from this function, and the user prompt, which is our actual user chat messages. That is, what is the weather in New York? So if we use OpenAI API right here with the given messages and the given tools, then we're going to have the response. So the content of this response, or like the message here, is printed out right here. So as you can see, the content is empty of this message is empty because no actual text is generated from the GPT, but rather we're going to have the attributes, that is the tool calls. So the tool calls right here include all of the tools that will be executed in this round. So you will have the function that includes the data, package of data that I mentioned earlier. So it will include the name of the function, that is get weather information, and you will have the arguments, which are presented in key value pairs, kind of JSON formatted data, string data. And apart from that, we also have the ID for the tool calls. So this ID will be necessary when we generate results and match the result to the corresponding tool calls. So first, let's get all of these important information out like this. And then we actually call the function with the given parameters or arguments. So we have the function, we get the function from, in this case, just getting the function from global parameter variables, that is with the function name, and then execute a function with the loaded function parameters. And we have the results right here. We check the result, and it's exactly the mock data that we have in the function. And now that for the next step, we're going to first add this tool call into the messages, into the prompts, back to the prompts. And then we also add a new message into the prompts that is the result of this tool call. So the role here is going to be the tool, and the content is the actual results. Another important attribute that I mentioned like last time is the tool call ID, which will have to match the ID in the response tool call. So after we add these two messages into the conversation, we again prompt the chat completion API with the new messages, and then we get the result, or like the response. So the response this time is going to be the text, that is the interpretation of ChatGPT for the current results that is added previously. So now the content is going to be a single text message, that is the current weather in New York is 25 degrees Celsius with humidity of 80%. So essentially you have 5 steps in this process, that is generate tool calls and then add tool calls to conversation, and then execute a tool call in the system with given names and arguments, and then add back the results and regenerate a message with the updated conversation. Next is the problem of executing tool call in the system or global environment. So previously, we execute the function just by checking the global environment for the function name. However, this will not work if we have imported functions from other modules, or we have multiple functions, or we have API, something like that. So here is some utilities or like implementation details to actually execute in a system global environment. So first, we're going to use, rather than globals, we're going to dynamically import the function from the module. So for example, the wet weather function is going to be defined in this module. So the module is root module is going to be main, and then just get attribute from that module. Another way to execute a function is as demonstrated in the graph earlier. If the actual execution here, the direct execution fails, then we're going to have a wrapper function which uses almost the same arguments as the function itself. So you have function name, you have function parameters, but it also include the metadata, which is any high-level data that is not generated by GPT, but is set at the start of the tool definition. So, for example, the module. So here is an example of this high-level data in tool schema. So here we have the normal tool schema, and then we have extra high-level information. For this case, we need the module name to dynamically import a function. So we have the module name as metadata, and we also have the fixup function. And then essentially in this section, we just have some symbol functions to actually form messages or print messages in a good and interpretable way. So these are some extra utilities. And then in this modularized execution function, here we are like combining all of the previous steps into a single function. So here, this section is going to be the execution section. That is, we're going to take the call that is a single tool call and then extract information and execute a function. So we can extract the name, we extract the arguments, we extract the metadata, and then we execute it by first trying directly importing the function and module and then execute it. And if it fails, then we're going to try to import the fixup function and then call this fixup function with the name, metadata, and arguments. Finally, the last function here is to reformat the tool, the results into nicely JSON formatted data string. Now for the whole operation itself, we combine them all into a single complete function. So the complete function will text in the list of messages or the prompts, and then it will also text in the list of tools. Then it will first generate this first response, and this response may include the tool calls. So if it includes the tool calls, then we're going to execute the tool call for each tool call that there is and add the result into the list of messages. Then finally, if it does include the tool call, then we're going to recursively call this complete function again to regenerate the response that is the interpretation of the results by GPT. Finally, it's just return the role and return the content of the last message. So here is how it is going to be done. So I'm going to have these messages. First is a system prompt. Right here, it's the same prompt as before. And then we have the user prompt, what is the weather in New York? And then see here, I just call a single complete command with the given prompts and the tools as defined earlier, and then print out the results with the tool response. So first you see the system prompts right here, and then you see the user prompt. And then for the assistant, now it just calls the tools. Here is the broad the results from the tool and return the final message. Okay, so that's the core function of our module, that is the function execution by ChatGPT tool calls. So now we're going to move on to the preparation steps. So how can we generate a GPT compatible schema? So the first module, submodule, is the function to tool schema. So if we have a function that is well documented, then we can extract the information about the function itself without explicitly defining a new tool schema. So the process right here is still, there's still some things to improve, but the current process is something like this. So you will have the function, and then you can extract the parameter description with something like AST library. And you can also use type hintings and then inspect library to extract the parameter types. So the Python parameter types will be converted into GPT compatible parameter types. You can also have the metadata extracted from the basic properties of the function, like name, like description, like module. And then all of these will be combined into a single function schema. And then you can also add some extra information if if it's necessary, like a fixed function, a service name, or any extra metadata. So let's return to our example function, that is get weather information. So you see right here from the function definition that this function is actually very well documented. So for each, you will see that it has, for each parameter, it has a type hinting right here. And it's followed by an inline comment of what this parameter is about. So for example, city is string, and the description is name of city. Zip code is type optional string with the default value being none, and it's a zip code of the city description. And it also has an overall function description right here. So we can try to go step by step to extract the information from this function in order to form a final schema. So first, with the parameter descriptions, we just use AST, and then we walk through the parsed source code and just split the inline comments. So in this case, we're only implementing it for the inline comments, but it can be developed further for any style of commenting. But the final usage is something like this. So you just need to input the function itself, and it will return the parameter description in key value pair. So city, the parameter name city is going to be described as name of city, and similarly for zip code. Next, we're going to have the type hinting right here, parameter types to type hinting, but we are going to implement the type converter. So the type hinting, it will return, when you inspect it, it will return Python parameter types. However, this cannot be directly transferred into acceptable data types expressed as string in GPT compatible tools. So here's the utility function for it. So for symbol types, it just use direct mapping. For a list or union type, it use recursive to continuously find the type of the sub items. And then for example, non-type, then it will return a single description like this. So type is null, and description is that a default value will be automatically used. So when you input this parameter type and description, then it will return the whole description of the parameter that GPT will use and interpret. So for examples usage right here. So the city parameter is going to be type string, and then description is name of city, and the return descriptor for GPT is going to be like this. So JSON formatted data with type string and description name of city. And for more complex type, like optional string right here, it will return any of first is type string with this description, or type null to description with value will be a default value will be used. So next, we can combine all of the previous utilities into a single function to schema function. So first, you can see that we extract the metadata from the function, and then we start to inspect the parameters with first the descriptor with the comments, which extract the comments from it. And then we extract the parameter type with annotation and convert them, and then finally add them all into the single parameter schema. Lastly, we'll build a final tool with a function. For function, you need a function name, you need the description, you have the parameters as extracted above. And for the metadata, you will have the module, which is the function module, and then service name, which is inputted right here. So for this function, for extra utility, you can add fix-up function or any additional keyword arguments as metadata in this. and fix a function here. So the test result, test without current function. So you see that I just need to input the Python function itself and add an extra parameter service name. And then the generated tool schema is like very similar to the original manually defined tool schema that we see in the previous notebook. And simulated GPT workload, I just test again with the complete function and similar prompt. But in this case, I automatically use this auto conversion and form the tools schema from it. And then it just have you the same results right here. Okay, so that's one route. So that is the route of going from function to GPT-compatible schema. However, you can also have another route, which is generating GPT-compatible schema from an actual API service. So for this to work, you will need an API service that provide the Open API specification file. So OpenAPI specification is kind of a standardized format to describe and document RESTful APIs. So in many services, like those generated by Fast API, that is OpenAPI spec file is a given. So usually we can have the OpenAPI specification file, and then in this process, we're going to first download and parse it as a Python dictionary. Then we need to do two things. So first is deep reference extraction. So in OpenAPI specification file, they use a type of that's called like referencing to store the data models that is going to be the inputs or outputs of your API endpoints. So these are stored like here. So this is a downloaded file, and it's stored, these schemas are going to be stored as component schema, and then each of these are going to be a separate data model. And then you need to flatten or expand this data model in order to convert them into GPT-compatible data models. And from that point, that's one side. And then you will also need on the other side to parse the endpoint configurations. So the endpoint configurations are stored as each value of the paths. So the paths are API endpoints, and in this case, each API endpoint is considered a tool for the GPT tool call. So you will parse the endpoint configurations, and then from that, you will get the parameters, which are of three types. So you have path and query parameters, and you also have the request body. The GPT compatible models are going to be attached to these parameters. You will also have the operation ID, or you will can generate it from the API endpoint itself to form a function name to be called as a tool. And then you will have the metadata necessary for executing this request. That is the URL and the method. So this is the URL, for example, API/v1/passenger information/active. And then the method is get. And from that, we form a schema. But also in this case, we have specifically implemented a fix-up function to generate requests to the original API service if after a tool call. So this is the first step to download OpenAPI specs. So there's nothing really complicated about this part. We just download it from a OpenAPI spec URL files that usually ends with like openapi.json, and then we save that and then parse it back as a Python dictionary right here. So this is an example of a single path endpoint. Next, we go to the deep reference extraction. So this one is quite complicated. So, but to save time, I'm just going to mostly demonstrate or like explain on this graph right here. So you have the OAS components. However, the problem is that usually you have the nested components. That is the definition of one component right here also includes the definition referencing to other components. So we're trying to flatten this problem, this component. So first, the implemented algorithm currently is first reversing and then gets the all reference list. From that, we also get the nested reference location. So where are these reference get referred to again in the components, and you will have also the nested reference dependencies. And from the dependencies, we check for the clean references, which does not include any dependency, and compare that to the reference list. So if there are still references that are not clean, then we return to this reference resolution and attach the clean references to these found locations. And we update the dependencies and then repeat it. If all references are clean, then we return the flattened component. Or if the number of clean references does not change, or like no more clean references can be extracted, then we also return the flattened component. So these are the actual implementation itself. It's quite complicated, but it's still the same idea. So I'm gonna briefly just pass through this section. And
Can I can I
yes.
can I stop now? I think I will cut this Q&A part later to edit for before publishing. But maybe it's a good time to ask for some any questions now, because I think it's really good, really well prepared. But I think the volume is quite a lot, so the people might not be following so well, and it's better to give some break and some questions. And okay, I can start with, and one is that you said that flatten the schema. That's also can this solve the circulation if the schema is referring to the same schema in it? Does it also to be
No.
solved?
So no, this cannot resolve it. But the reason that this approach is chosen is because usually it has the kind of this kind of circular definition. So that's why if we use a normal recursion, then it will not work because it's going to go to circulate. So that's why this reference list also is chosen, because it will check if the number of clean references doesn't change or no more clean references are there, then it's going to just return the flattened components. So it still work in our context is because usually in the inputs or like input side, you have the path or query parameters, which definitely does not have circular definition or request body, but a request body is still quite rare for it to use this kind of nested or like not really nested, but a circular definition. But rather the circular definition in at least in row DG traffic, it usually occur in the output side, not the input side. So it still currently work, but we can definitely improve.
Okay, thanks for the clarification. And maybe I think the others should ask any question. Otherwise, if you not if you don't get the point right now, then it's getting harder to follow the rest of the talk.
Yeah. Well, I have this might be a bit primitive question, but it's related to the first part of this. But so like how GPT knows the exact function it has to call when it gets the input. For example, if user types something get he wants to know weather, then how GPT knows it has to call get weather function. I understood how parameters are extracted, but I didn't understand how the exact function itself is.
Yes. So basically that will depend on these tools. So we're going to need a tool schema to be fed into the GPT before any messages are prompted. So the tools are explicitly defined here with the function name. And the important part here is also the description of this function. So it will, at the start, it will automatically interpret not only the prompts of the user, but also the tool schema. So when interpreting the tool schema, it tries to understand the description and the name, and then it matches it with the prompt. So that's how it choose the correct function to call. And so it depends entirely on what tools are you defining in this tool schema that is fed at the beginning.
Okay. Yeah. Then
Also, also, I think that it should be explained about how and who has the responsibility to execute the function and to get the result back to the GPT.
Yes, so the GPT itself, it will stop as at the tool call. So it will generate this pack of information right here. So it only have the information itself, that is which function and arguments it decides to go with. But the execution itself is from outside. So the execution is implemented from outside in the system. So that's how we execute right here. We manually extract the parameters, the information from this package of information that GPT returns, and then return the results by executing in our system. And then the GPT, we call GPT again to interpret the generated results.
yeah. Yes.
So
Thanks.
yeah. So important point is that I think most important part is GPT doesn't execute any function, but they will
Yes.
ask us to execute, and we
Yeah.
are the ones responsible for execution and get the result back to GPT. So then the rest is gonna be still continued by GPT. I think that is the most important part, and which is called function calling. And at least if you understand this part, then yeah, you can still continue to follow, I think.
Yes. So are there any other questions so far?
Then I also missed like how fix up function is used exactly. Do you have some example, for
Yes.
example, for
So,
get do you have some example for example fix up function for get weather function or any other?
yes. So essentially for the function itself, if you have a Python function, usually we don't need to use a fixer function because we can directly import it and then use it. So, but in this case, for example, what I was continuing here, that is the open API, then we need a fixer function to actually call the original API service. So can I continue to like
Yeah.
explain to see how it works? Okay, so this is the deep.
Just a moment. I think API, which Ni said here, is a REST API. So which is not a normal Python function, but it's a web API, so which cannot be directly called. So that is she said here API.
Yes, that's like a back end server with you call with some URL. So that's yes. So that's the deep reference extraction. So this is quite specific to coding and open API specs. And then again, we have the open API schema to GPT compatible schema, but I will probably best explain the auxiliary fixer function first, since you were asking about it. So here you have the different types of inputs that you need to generate a request by Python. So you have the parameters that GPT will provide, including the path, query, and request body. So these are like flexible parameters that GPT will configure and put as arguments for your function or your tool call. However, there are some other fixed values that you will need for each endpoint. That is the metadata, that is including the URL and the method, HTTP method for each endpoint. So this is why we cannot like directly execute it, but we're going to use a fixup function. So in this case, the fixup function will text in the function name and then the metadata, that is URL and method, and then the parameters as described by GPT arguments. So this is another metadata that is mostly there for implementation simplification. So it's accepted queries to differentiate between path and query parameters. But here, as you can see, we just, these are the parameters that GPT provides, and these are the metadata. So kind of a strong point of a fixup function is that it can use the metadata instead of just a single original data. And there are some further function when we go to the store or notification frameworks. But in this case, it just if the original function importing fails, which it does fails in this case because we don't have a specific function for each endpoint, then this fixup function will be used. And for currently, it just generates the request based on the functions or like the parameters that we have. That is the method, the URL, the parameters with the queries, and the JSON body or request body. And then it just return the JSON. So if you look at the implementation of execution right here, then it's just, so this is the directly. So you just call the function with the given argument. And if it fails, then it use fixup. That is, you call the function fixup, the fixup function with the name, metadata, and arguments. So are you following?
Yeah.
Okay. So I would
I think can you also explain about why we don't use the we didn't implement the function, but we use this way.
So basically, this is for dynamic importing. So if you so there are two approaches. Initially, that is, we can try to write the function itself in the API with the given API, or we can go with this method that is to use a fixup function to generate a request. So basically, the other method was first is quite clunky, and it's requiring you to write the function and save those functions into the system itself. And then it may lead to, for example, same functions with the same name, or there can maybe some storage issue and cache issue. But if you use the this method, then it doesn't exactly need to save the function definition, but it just needs one single fixup function for executing all of the requests from all APIs. So there are two methods, but we decided to go with this one. Okay, so I'll briefly mention the GPT schema to GPT OAS schema to GPT compatible schema. This is because even though they are both JSON formatted data, the OAS schema supports a much wider range of fields, but GPT only supports certain specific fields, recognized field, including these. So the way that we implement this is that we just define some directly transferable properties and directly translate it to that. And then we just save any additional properties into an additional mapping like this, and then add it directly into the parameter description. So one example here is the complex parameters from DT traffic endpoint with the description like this. So name X minimum, and then it has the extensive schema of something like this. So we're going to translate it. When you use this function, then it's going to just leave 3 recognizable fields, that is description, type, and default value, and everything else, including the maximum value, exclusive maximum, minimum value, format, explicit format, into the description itself. So these are some other like utility. These are some important utilities, and finally we just add combine all of the previous process into a single function, that is API schema. So this function will text in the base URL to create the final like URL later for the metadata, the open API schema as Python dictionary, the service name, and the fixer function, which is also defined previously at generate request. And it just extract all of the endpoints from the path parameters of the original open API schema. And then for each method, it defines the name, get description, and defines the parameters, and of course, get the accepted queries. Parameters, body, request body, these are all parameters type. And then it just return the final like function description for each endpoint, including the name, description, parameters, and URL and method, and accepted queries as metadata. Oh, sorry. And it add fixed function and service. So example using this is that it just here you see that it just adds a single tools. It just forms it with a API schema, and the base URL is DT traffic URL, and with the extracted OAS, and it just prints out here is the first function, which is getting the weather data history, and the all the formatting seems correct right here. And you also have the URL method and service right here, and the fixups is our generate request function. Simulated GPT workflow, you can, with this given tools as defined here, you can prompt, the user prompt is to get weather camera information from stations with ID this and this. So it will calls the correct like URL endpoint, and extract and interpret the whole results as this. So you can see the name, station ID, name of station, location, coordinates, and camera types, and all of the information that DT traffic has saved and returned. All right, are there any questions about this core functionalities?
So I think you should bit mention about the metadata is the custom extension of GPT function calling.
Yes, so metadata, so both you have the GPT itself only goes from here to here. So you have the type and you have the function, and then in function you have name, descriptions, and parameters. But for our current usage, we also add some extra fields, that is the metadata. You can include any extra information there. And the fix-up function, which is the kind of fix up if direct execution fails. So these are our custom fields. Are there any questions? Okay, so I think I will move on to the next one of the utilities that get added as a tool in our framework, that is the utils model. So I will go over the ones that is more complex in the utility module, that is the store and the notification, to explain this one. So the store utility is essentially the goal is to dynamically add the functions and new tools into the existing tool list. So the problem with this is if you look at the complete function, then it just takes in a Python instance of the tools at the beginning and then go with it for the rest of the operations. So these have some problems if we want to dynamically create new tools and add it to it. So basically, first, our complete functions use a tools instance at the top level and does not pass this Python pointers to utilities for function execution. And then you also have the tools management should be dynamic and operate in real time. It means that the calling interface for calling the complete should not change during application runs. And then lastly, one considered but failed like algorithm is to pasting the tools as text in messages for GPT to interpret. So the problem with this is the maximum token that GPT allows. So, and also GPT may not reliably interpret the resulting tools. So here is our so the solution for this store utility is to create a framework that allows a function to manage the top level tools. So we can define a kind of a fix-up function to retrieve the tools from the global environment with appropriate metadata and pass in the tools for any subsequent operations. So first we define the base operations, that is the add function tools. So this will text in the tool list that we're currently using. And then it will just generate the tool from a function or like a list of function name. So this list will dynamically import the functions as specified in this list and then add the generated schema of that function to the tools. So we just add like this. So LLM, for example, we are using some adding some functions from the vision module, that is llm.vision.youtube live, and then this function itself capture YouTube live frame, or next is askGPT4. So the generated tools is going to look like this. So all of the functions parameters are correct right here. And also you see the metadata. The module is LLMCAM.vision.youtube live, and service is this. And you can see that the tools are defined at the beginning, which is considered like top level instance. And then it is updated when we call this function right here. Next, similarly, we have the dynamic API installation. So there's not much difference. Essentially, you just text in the tool list.
I think you should a bit clarify the terminology of function and API here.
Yes, so a function is the Python function that is installed via a local library like default utilities such as math, square root, random, something like that. And then any functions that you installed from any PIP libraries, like, for example, our own LLMCAM library. So those are like Python functions that can be imported with Python code. And the API tools are the ones that are retrieved from the web service, any backend web service with OpenAPI specification, such as like the one on Digitraffic API endpoints, or any other online API functions that you will need to call with Python request. Yes, so essentially the add API tools operates almost the same way. So you just need some different parameters like a base URL, and then the OAS URL, and then OAS destination, which is optional, saving location, which is optional. So it just use the previous functions to generate the schema and then extend the existing tool list by it. So here's the use case. So here I add a new service from the Digitraffic endpoint. And then the tools, the high-level tools are also updated with all the tools that is generated from raw Digitraffic. And then here's the basic implementation for removal of existing tool. This removal is done with the service name, so it will remove any tools with the corresponding service. Okay, so here's the main part of this utility, that is the framework itself. So the fix-up setup. So you have the fix-up, but you will need to attach this tick fix-up function to the tools instance, the high-level tools instance that you need to manage. So instead of explicitly define a generic fix-up function, we define here a core function. So the core function will have already the tool list right here, and then it will check for the function name, and then it will operate the function that is the handler functions, that is the add API tools, add function tools, or removal of tools, and it will pass in the tool list to the found function. So the handler schema is also defined right here. So the handler schema basically is just a function schema, but it has some fix-up, but it has the fix-up function, and it also like remove the tools from the parameters to ensure that this function will fail so that the fix-up function will be called. And here's the example usage. So you have the tool, the high-level tools instance, and then you attach the fix-up function, like you define the fix-up function that is attached to this tools instance. So anytime this fix-up function is called, it will explicitly call this high-level tools instance right here and pass into core handler function. And just extend the tools right here, and then from this point on, it should have all the handler tools, that is the adding functions and removing functions. And then you can like try to execute the handler with the handler name, the module name, and just like any extra parameters that is used for this function. That is, for example, here we add the row digit traffic. So you should input the base URL and the service name. So now the functions should be updated with new API tools, and you can check the fourth one, which is the new function, is going to be an endpoint that is generated by digitraffic, row digitraffic. And here's the simulated GPT workflow. So you have the tools. Again, similarly, you have the tools. You have the defining the executor handler function attached to this tools instance, and then you update this tool with the handler functions, 3 handler functions right here. And then we try to add a new API service. So I explicitly, the prompt, user prompt, is to add new API service with this service name using the base URL of this and with the open API specification URL of this. And then it just executes. It says API service has been successfully added. And now if we check the length of the tool list that is right here, that is passed into the complete function, you will see that it's updated to be 65, which means that it has already included all the functions from this service, from this newly added service. And then if you try calling the exact same prompts that we previously used for the open APIs to schema notebook, then you will see that it has basically the same results, yielding the results successfully. And you can also remove it. So if you try to remove it afterwards, then if we check it, then it also removes successfully with only 3 remaining handler tools. Okay, are there any questions about this section? Yes, then I'll move on to the notification, which is similar to store. So this is also a function that should be called by GPT as a function calling, but it also operates with the framework idea, not explicitly defining any set execution handler or any specific functions, but it uses a framework instead. So this framework is a little bit complicated. So the idea is that we need to send notifications. However, because this monitoring process will be initiated with the user via chat UI, so the condition for sending the notifications or stopping this monitoring stream is not constant. So we try to dynamically check the conditions by also using nested GPT function calling. So the task itself is demonstrated here. So when the user prompts the main GPT with the notification task description, it will not operate or check the condition right away, but it will start a separate thread that will have started this notification stream. So inside of this notification stream, it will pass the description that it is the user messages to the sub-GPT, and this sub-GPT will check the condition as described. This sub-GPT is also supplied with a notification sender as a GPT tool, and also a stream stopper function as a GPT compatible tool. So after it's checked the condition, then it will decide whether to use any of the tools that has been provided to either send notification or stop the notification stream. So if nothing happens, then it will just continue looping with the notification stream until the stream stopper condition is called. So this is the idea that we are operating with. So an example is that we have a random generator right here, which generates any number between 1 and 100. We have a simple function for sending notifications by just adding it to a high-level notifications list. Now for the start notification stream, we kind of so the first we generate a subtools which also include a function to send notifications, and then it will just loop through this whole loop. And for this demo, we only loop through 5 loops, and for each loop, it will call the complete functions to allow the GPT, sub-GPT to check the conditions and decide whether to call the send notifications function. So this is the demo, and then afterwards the notifications are checked. So now the empty list is updated with this whole 10 notifications. So then we modularize it with a separate stream thread in order to execute this monitoring stream parallelly to the main GPT. And then we have the framework right here. So it's similar to just this different in this case is using the while loop until the stop event is set, which is not called until the stopper function is called. And now we are moving on to defining the stream stopper. So instead of this is the default stream stopper, but the application itself can define any different stream stopper. So alongside the stream stopper function, we also have the stream starter. This is because usually the context for stopping the stream or like the necessary information will depend on the context of starting the stream. So in the default stream stopper or like a default setting, we just define a new variable, global variable called stream thread. And then when the stopper is called, then it's just stop that specific stream thread. So, and now we define the core function rather than a hard-coded stream function similar to the store itself. So in this core function, we copy the sub-messages and we extract the tools schema that include the stream stopper and the notification sender schemas. And then we add those tools into the subtools, and we start a stream with this subtools and sub-messages. So notes here, because the function to schema is yet quite primitive in type, so the messages cannot be passed in safely unless we specifically manually specify the messages to be the GPT compatible messages that include the role and the content of the message. Next is the most important part, that is the simulated GPT framework of this specific setting. So first, we're going to need a tool, an existing tool like the random generator. And then we need a default function, kind of a simple function for sending notifications that is just adding to this notification list. And then from that, we define a start notification stream, which will text in a single parameter that is the message list that includes the prompt or like the description of the condition from the user. And then it will, in this specific setting, we just use the notification stream core, and we add in the stream starter is the default stream starters and default stream stopper right here. And we also add in the send notification right here. And from that, we continue to add to the tools. That is adding this tool start notification stream right here. And then we start with the prompting. So the prompt notes that it has to be more specified in this system case, so that the performance is more consistent. If asked to monitor and notify, do not resolve in the main thread, but return to a subactivity in notification stream instead. And now I just prompt, can you notify me where every time you generate a number higher than 50, stop after 10 notifications. So it's essentially, in this case, you are like, this message will be returned immediately, but it will, in the background, it will operate with the stream thread right here. So after a while, I check, and the notifications now include 10 messages with the generated number being higher than 50 and the length being 10. So it has stopped after 10 notifications. And I also check the global stream thread, and it's already stopped. Are there questions about this? Yes, oh, that's going to be the end of my presentation. So Lynn will be presenting tomorrow about the vision module.
Can I stop recording now?
Yes.